Hi, my name is Emmanuel Etukudu and I'm currently taking Physics 2212 at Geotech, and this is my lab report on circuits. So for the first part of the lab, we have a series circuit with two different resistors, two ammeters, and a battery. I found the ammeter readings to be the same for both the ammeters, and the values stayed positive even if I connected an ammeter backwards. If I replace one of the ammeters with a voltmeter, the current in the other ammeter is still the same, and the potential difference is 3 volts. And if I close this circuit and measure potential differences at different points, I find the results shown at the bottom of the slide. I found the sum of the potential differences across the circuit to be zero since the circuit is just one large loop. The fact that the sum of the potential differences is zero is in accordance with the loop rule. Here is a look at a diagram showing the potential difference at different points in the circuit. As you can see, the battery raises the potential. The wires don't really do anything as they are assumed to be ideal and therefore do not have any resistance. The resistors, however, lower the potential, which is why the potential difference across there's a potential difference across them, which as shown in the previous slide is negative. The ammeter does not significantly affect the potential as it is assumed to be ideal and therefore has zero very little resistance. Now for the questions. Why doesn't the addition of a voltmeter in parallel change the ammeter reading? Well, because the voltmeter has a very high resistance and therefore only a very small amount of current flows through it, so the current in the rest of the circuit remains constant. And also, what happens if an ammeter is connected in parallel with the 100 ohms resistor? Well, then both ammeters read 0.06 amps. And lastly, we were asked to calculate the resistance of various circuit elements using ohm. As for the RC circuit, when a bulb is connected in series with a capacitor and a battery, it starts off bright and then slowly dims until it turns off. The same thing happens if you connect a bulb to just a charged capacitor. It starts off bright and then slowly dims until it's off. And in both these cases, the current starts out large and then slowly decreases to zero, which is why the bulb dies out. The time taken to charge and discharge capacitors which were connected in series to resistors of varying resistance are also shown at the bottom of the slide. Now for the third part of the lab, the time dependence of potential difference across a discharging capacitor. My experimental data is shown here in the form of a table, and to the right we have the graph of the potential difference versus time, which resembles an exponential decay graph. If we linearize this data by graphing the natural log of potential difference over delta V naught, we get the graph below it. This is as expected in a linear graph for which you have the specific formula as shown at the beginning of the presentation. Also, when we applied this formula, we got a slope of negative 0.166. The RC value is negative 1 over the slope, so the RC value was calculated to be 6.02. Similarly, if we calculated RC by simply multiplying R and C, we also get 6, which is a reasonably close value to 6.02. And this could help us conclude that the experiment was successful and produced reason. Now for the what if questions. What if we have done this lab in real life and used an actual ammeter? What will be different about that, and how might this have affected our results? Well, an ammeter is designed to have very low resistance, so an ideal ammeter has exactly zero resistance. Of course, this is not possible in real life as all objects have some level of electrical resistance, and even the best ammeters have a small amount. Adding resistance to a series circuit just decreases the amount of current flowing through it. So had we done this lab in real life, we'll be getting lower than expected current values due to the internal resistance of the ammeter. And if we did the experiment in real life using a real battery and capacitor with no resistor in the circuit, our ideal model will predict that the capacitor will be charged instantly. This is due to the fact that the model assumes no resistance in the wires nor in the battery, and therefore an infinitely large current will be able to flow and will therefore charge the capacitor instantly. In real life, however, there's always a small bit of resistance in the batteries themselves as well as in the wires. So the capacitor cannot be charged instantly. It will be charged fairly quickly, but certainly not instantly as predicted by the ideal model. Thanks for watching.